So welcome to the People, Data Centers, and AI, oh my, where we're going to discuss the social, climate, and economic impacts of the AI data boom. So really excited to have a really fantastic group of speakers here today, and really excited to share this with all of you. Uh, oops, sorry, still working on my share mode apparently. All right, there we go. Okay, welcome. Welcome, everybody. As you come in. That's odd. Okay. So one thing we as people are coming in, we'll just get started in a minute here. How do you use AI in your social science work? Please use the chat and just let us know. How are you using AI currently in your social science work? Or are you not using it at all? Some people use it for transcripts. Some people use it for in their data mining or in their how they write. So please go ahead and include that in the chat and we'll take a look to see avoiding for environmental reasons. Okay, not at all. Don't use AI at all. Not at all. That's fine. Um, Good transcripts, data analysis, code development. Not at all. Yep, not at all. Okay, that's great. Pressure testing, not worth the cost. Agency doesn't allow us to use it. Okay, only in limited circumstances. This is very helpful. Research, technical details of contracts. All right. Yeah, thank you for your input here. Code development. All right. Fantastic. Great. So I think we'll go ahead and start. I want to just mention that this webinar is part of the BECC Community Exchange Series in 2026. So the last Tuesday of the month, we've already had two. We've had one journal club and one lean coffee. Now, journal club is where Beth Carlin is leading this, and she will send out a academic journal for people to read, and then you hop on at that July 28th is the next one, and you will split into small groups and discuss it. There's also Lean Coffee, where it's more democratic in terms of choosing the subject that people want to talk about. So the next one of that is August 25th, and our next webinar will be September 29th. Okay, in terms of protocol, please go ahead and use the chat for discussion throughout the webinar, and then use the Q&A feature. You see that sometimes you can't see it. It's in that circle with the three horizontal dots. If you click on that, you'll see Q&A, and please use that for questions throughout the webinar. We are going to have our presenters present one at a time, and then we'll have questions. We should have a good 20 minutes or more questions at the end, and then the recording will be available on the BECC website. So with that, I wanted to introduce our first speaker. Miriam Axel is and I will let Miriam go ahead and share her slides while I'm introducing her. Miriam Axel works on sustainable transitions, climate resilience, environmental justice, and the intersections of energy, water, and emerging technologies. She is a researcher at the United Nations University Institute for Water, Environment, and Health. And she is a lead author of this UNU INWAY's report, Environmental Cost of AI's Energy Use, Carbon, Water, and Land Footprints. She holds degrees from McGill University and Imperial College London, where she completed her PhD in environmental policy as a presidential PhD scholar. So with that, I think I will let Miriam go ahead and share.
Thank you so much. Are you able to see my slides?
Nope, just seeing you.
Okay. That just had them up. I think it's funny how we're talking about all of these advanced technologies, and yet it's often the simple things that in your slides to share that are the complicated ones. I'm also really interested to see, while I'm pulling my slides up, people's reactions to not using AI. I think that's one of the things that is I find really interesting is how it's just integrated in almost everything now, from things that we don't see, like spam filters in our email, to navigation systems. Also appreciate the comments about not wanting to use it because of the high energy cost. That's something that I'm going to be talking about today, and particularly the differences in types of AI usage and how that impacts electricity use. So,
It's showing the slides really small, Miriam, and then a picture image of you.
how about this? Are you seeing just my slides?
Now we're seeing the image of you and your slides.
Okay.
Miriam, would it work if I showed your slides?
Yeah, that would be great if you don't mind.
Okay.
Thank you.
All right. How's that?
Oh, wonderful. Thank you so much. So first of all, I'm just really delighted to be here. Thank you so much to the organizers, to all of you for joining. I'm very excited to talk about this. I think this is a really interesting issue, and I'm coming to this as Therese said, as a UN researcher. I'm at the United Nations University's Institute for Water, Environment, and Health, also known as the UN's think tank on water. It's one of 13 United Nations universities institutes globally. And as a longtime lover of BECC, I'm really excited to present to this audience. So please welcome conversation in the chat. Really love how BECC is, I think, one of the few audiences that always has such an engaging and active chat. So really, really looking forward to your questions. And thank you so much for this opportunity to be here. So I guess I was going to start with who's used AI today, because I think it's such an interesting question that it now is integrated. I think it's almost impossible to avoid AI. There was a comment in the chat about trying to avoid it, but it's in Google search, and I think that's a really interesting point because 10 years ago there was no AI integrated into the summaries on Google search. We now have, there's an estimated 16 billion Google searches every day, and it's gone from around 10% of Google searches had an AI integrated into them a couple of years ago to 50%, and now that number is getting much closer to 90%. And I think from a behavioral standpoint, that's something personally, I just turned off the automated summaries on Google search. I think often they're not the answers that you want. And so I think from a behavioral perspective, there are a lot of levers and decisions that we can make as individuals, but it's very difficult to avoid AI. It's in almost everything now. So I think what I'm going to talk to you about today is our research on the environmental impacts of AI, and this is as a function of electricity. Our study was looking at the the carbon, water, and land footprints of how the electricity used to generate or run the data centers that are essentially the backbone of AI, and how those differ geographically. So if we could go to the next slide, please. So first, I think the question here isn't, whether AI is good or bad, but rather, do we do all of the functions need a large generative model? What's the modality? There's a massive difference between text generation. Simple things like a spam filter has kind of the lowest electricity usage, and what our report looked at was how the level of electricity usage translates to carbon, water, and land footprints as a function of how that electricity is generated. And maybe here I'll stop and give a quick comment on our methodology for the report before I dive into it. So what we're looking at is the environmental footprints that are associated with the electricity use that's both to train and operate AI systems and powered data centers. So we don't measure every facility, or we don't provide life cycle assessments of every chip or server or building, which is very important, but that was not part of what our report was looking at. So our core calculation is electricity demand multiplied by a life cycle footprint intensity. In other words, every kilowatt hour of electricity has a carbon, water, and land footprint based on how that electricity is generated. And the core point that I'll be highlighting is that something that is low carbon electricity, such as hydropower, might have a low carbon footprint, but doesn't necessarily have a low water footprint. And the same thing for land. So there's been a lot of conversation now about carbon accounting, which is really important, but that often ignores the water and land footprints. And also another point to clarify is that I think there's been quite a lot of positive conversation in media and understanding of the very high water footprint or water usage of data centers. Our report doesn't look at the water usage for cooling data centers. It's only the water footprints of how electricity is generated, which means that the numbers that we're highlighting for water usage are actually a lot higher if you include the cooling that's used for cooling data centers. So our main analysis is focusing on carbon, water, and land footprints of AI's electricity usage, and we're using data centers as the backbone for how AI is generated. So with that, I think that the key point here is that when we think of, at least when I think of the cloud or AI or data centers, the cloud sounds very ethereal. It sounds very immaterial, and I think that the point that I'm trying to highlight is that they have AI and data centers generally have a very physical footprint, and so the main goal of our report was to highlight the very physical footprint of AI. So with that, can we please move on to the next slide? Right. So I think here the point is that AI has it's material infrastructure. It's not just software, and I think that's kind of the framing shift that I want to emphasize from a behavioral standpoint. That the cloud has a physical geography and a social geography. So behind every chatbot answer, every recommendation that we might not even be making intentionally, when you use Google search or you go on Netflix and you get recommendations, those are AI generated almost entirely now. And there's a very physical geography to that. Behind every recommendation system, there are GPUs, high performance processors, electricity generation, cooling systems. So AI is not just code, it's copper, it's concrete, it's silicon, it's lithium, it's water, land, and carbon. And a lot of those materials come from countries in the global south. And then at the end of the life cycle, there's a very real risk for the physical impacts are sort of throughout the entire life cycle. And I think here there's kind of a key justice question, which is that inside every AI system, despite sounding ethereal and sounding like the cloud, there are very physical supply chains in local places. And the local places might not necessarily be the ones that receive the economic benefits. So there's this kind of, from a justice perspective, a mismatch between distant benefits and local burdens. And I think that's kind of the central environmental justice and behavioral question here. So if we could go on to the next slide, please. All right, so thank you. Before getting into the numbers, I want to explain the methodology. So we start with estimates of electricity demand. We use public data sets. So these are from the International Energy Agency. And then we're translating those. We looked at 194 countries, and we translate that electricity demand, how every country is generating their electricity, into environmental footprints using footprint intensities for electricity generation. So the basic structure is that electricity demand multiplied by carbon, water, or land footprints gives the overall associated footprint. And we take both a global average and then we look at country-specific averages. And so this is a function of only how the electricity is generated. And for the country comparisons, we're not looking at local differences in electricity. So this might mean that electricity generated in California would be quite different from electricity generated in Virginia versus others. So we're only looking at an overall country average. So there's a lot of granularity that we're missing in this methodology. This is just overall country usages. And we're also not looking at specific data center hubs. And I think the key point here is that when we look at national electricity mixes, the same kilowatt hour can have a very different implication based on where it's produced. And this is where the water clarification matters because we're not saying that a particular facility withdraws all of that water. It's solely a function of how the overall electricity in that country is 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 um, is being generated and the water footprint of how that electricity is generated. And I think this is probably the next step is to look in greater detail at where the differences on a country level are, and specifically on a facility level. But this is just an overall footprint method, not a facility, not a full life cycle assessment. So with that, I think the key point here is that data centers are becoming a really important energy planning issue, and the scale of data center electricity usage is now large enough that it has to be treated as an overall energy planning issue and not a niche digital sector issue. I think we're starting to see a lot more discussion in the media and public opposition to data center development, which I think is highlighting just how important this issue is. So in our report, we found that global data centers were estimated to consume 448 terawatt hours of electricity in 2025. And that means that if we treated data centers as a country, data centers electricity usage in 2025, they would rank around 11th globally by electricity consumption. But they're projected to double by 2030 in the next 4 years to around 945 terawatt hours. So that's close to 3% of projected global electricity, which doesn't sound like that much. But if we think about that as in terms of tangible and maybe from a justice perspective, in 2025, the electricity used by data could supply the annual residential electricity needs of the entire 1.3 billion people population of sub-Saharan Africa for over 2.5 years. And by 2030, the amount of electricity used just by data centers could supply that same population of 1.3 billion people for 5.5 years. So the point is that isn't to say that these electricity systems are directly interchangeable, but rather to show that the scale of demand is really entering some of the highest consuming on the scale of country levels. By 2030, that would rank sixth by global electricity consumption, just behind France. So these numbers are really staggering and growing quite quickly. So if we could move on to the next slide, please. So here, the point that we're trying to highlight is that carbon accounting alone isn't enough. Low carbon electricity is not automatically low land or low electricity. And we look at how the carbon, water, and land footprints behind every kilowatt hour have multiple environmental dimensions, and these don't necessarily move in the same direction. So a coal-heavy grid would have a high carbon footprint, but not necessarily a high water, high land footprint. A hydropower heavy grid would have a lower carbon footprint usually, but a larger water footprint and often a larger land footprint because of reservoirs and evaporation. Bioenergy can reduce the carbon footprint or the carbon intensity, but also have a much larger land and water demand. So our methodology isn't really asking just how much electricity AI usage consumes, but where that electricity comes from and what the trade-offs are. If we're trying to move towards decarbonization, what are the other environmental impacts that might be being caused as a function of that? So, and I think here the key point is when we're looking at data centers, two identical facilities can have very different footprints. If one is powered by a whole coal heavy grid and another is powered by a hydro or nuclear heavy grid. And the practical implication here is that AI and data center sustainability should should report electricity, carbon, water, land, and local context and local justice issues together. So a single carbon metric only can hide that sort of burden shifting. So if we go to the next slide, please. So here the main point is that the location really decides who feels the footprint. The geography of compute is really uneven. Over half of the world's data centers currently are in the United States. And if we look specifically at the AI-capable data centers, only 16% of the world's countries have AI-capable data centers. Those are capable of either training AI models or operating inference or the queries to things like ChatGPT and Claude. And 90% of those data centers are hosted in just two countries, the US and China. And so I think here the justice and behavioral question is who has access to AI benefits, who bears the local infrastructure burdens, and who decides what protections are required before new capacity is built. And I think especially for communities that are already facing water stress or energy insecurity or pollution burdens, or might have limited political leverage, those decisions are not abstract technology policy, but they're really local environmental governance and behavioral decisions. So we can go to the next slide, please. So just to quickly distinguish between training and inference. So training these large models has kind of captured the media's attention, rightfully so. But now at the rate at which these tools are being adopted, nearly 90% of the overall electricity usage of AI is from the inference stage, from how it's being used. So I think the key point here is that if we look at training ChatGPT 4 consumed around 70 gigawatt hours, and that's around the annual residential electricity usage of nearly 500,000 people in sub-Saharan Africa. So I think the point is to show here these training these models consumes a massive amount of electricity. But at this point now, based on how quickly these models have been adopted into everyday use, whether it's things like being implemented in Google searches or most new phones have an automated AI assistant, that number, the training is only the tip of the iceberg here. We can go to the next slide, please. So just to kind of wrap up here, I think not all AI tools have the same footprint, and we're trying to show the differences between a short text generation, something like ChatGPT, we're using as a baseline. So that's 0.047 watt hours. A typical large language model response, slightly longer, is 9 times the amount of a short text response. And then an image on average is around, and this is a relatively conservative image generation, not a high resolution image, 2.9 watt hours. But then a high complexity or an AI video is really sort of the new energy frontier here. And so that's nearly 9,000 times more energetically demanding than a short text generation. So not all AI usage is the same. And I think if we think about it in the context of everyday usage, a typical AI image generated uses enough electricity to power a 10-watt LED light bulb for about 17 minutes, while an AI video would power that same light bulb for 42 hours. So it's not just, we're not saying that we're anti-AI here. I think it's really important to understand the distinctions between different types of tasks and have a sense. And this, I think, is where it's really important for companies to be able to publish this type of information on the differences between these types of usage. So if we can go to the next slide. So I won't get into this because I don't want to go over time. But I think the main point here is that defaults matter. I think there's a lot of important there's an important role for companies to help publicize and make concise responses the default. It's not just on users. Users don't necessarily choose the model or the routing path, but the default quality setting matters. Video can have reducing the number of the lower resolution can have a big difference. And so I think it's both a behavioral question on the part of the users as well as on the model operators. And I think I'm over time here, so I think I'll wrap up with that. And there are just some re resources for future reading. Thank you so much.
Yeah, and these slides will be distributed after the presentation. So Miriam had put together a really nice set of resources there. Now I'm going to invite Camille to talk about the regulation that she's had her finger on the pulse of this for some time now. So I'm going to invite her to share her slides while I introduce her. Dr. Camille Crittenden, who is the Executive Director for the Center for Information Technology Research in the Interest of Society, or CITRIS, and the Banatao Institute. Dr. Crittenden is the co-founder of both the CITRIS Tech Policy Initiative, previously known as the CITRIS Policy Lab, and EDGE in Tech, or Expanding Diversity and Gender Equity at the University of California. Between 2019 and 2020, she chaired the California Blockchain Working Group, played a key role as co-chair for the Student Experience Committee within the UC Presidential Working Group on Artificial Intelligence. Ongoing leadership includes membership on the UC AI Council. I think I will stop there and let Camille go ahead and present. Thank you.
Great. Thank you so much, Therese. And it's a pleasure to be here. I appreciate being on this panel with Miriam and Wani. So as Therese mentioned, I'm going to speak mostly to some of the regulatory efforts around data centers, primarily here in California, but I think that those insights and those efforts really are applicable and will be increasingly replicated in other jurisdictions, other states, and perhaps even nationally. Some of the slides that I show, let me see, like this one might replicate a little bit of what Miriam presented as well, but perhaps just in a slightly different format. So you can see here, I think we're all familiar now with the story about the greatly increasing accelerated use of power and energy demands for data centers, primarily driven by the rapid expansion of AI and AI tools and models. So we're all here to talk about the environmental dimensions of the data center use, and there are a few things, generalities that I just wanted to put forward that Miriam has already mentioned some of these, but when I'm presenting these slides mostly for a non-specialist kind of audience, these are some of the things that I mentioned. So of course, energy demands, AI workloads are much more energy intensive than other kinds of computing. Water use, we touched on that as well. Where data centers are sited is really important to how electricity is being sourced for supporting those data centers and how renewables are being integrated into that mix. Of course, the considerations for environmental degradation, Miriam talked about land use, but of course, where those data centers are located can have a real impact on the local ecosystem, whether that's the natural habitats or residential neighborhoods that might be right next to a new data center development. But the constant noise, constant lighting, those can all affect quality of life for us and our animal neighbors. Also, the whole issue of embodied carbon. So you build these massive data centers, They have hundreds of computers with millions of chips in them. And then 2 years later, you have to replace them because there's the next generation of chip architecture that everybody wants to be on the cutting edge. But then what do you do with the old equipment? All of that should be taken into consideration. So it used to be a few years ago, not even that long ago, that people were excited about having data centers, not necessarily right next to them, but they thought, sure, all the benefits of AI that we're getting, of course, we need to have the infrastructure there to back it up. This was a question from the Washington Post a few years ago, mostly in Virginia, among Virginia residents. And Virginia, along with California, is one of the most intensive geographies for data center placement. So this was really a top concern for some of these Virginia residents. But even a few years ago, nearly 3/4 of people there thought they would be comfortable or at least have no opinion about whether a data center was in their community. Whereas then a short 3 years later, that sentiment has almost flipped. So we've really seen a difference in opinion recently as people are coming to understand more intimately the implications of having data centers in their neighborhoods. So in general, I want to point out just three directions for responsible scaling for us to consider. And these are some of the goals of the legislation that I'm going to mention in greater detail. The first step, I think, is really just to measure what it is that we're talking about, how much energy, how much water. And you might be surprised to know that that's a difficult question to answer. And companies are not eager to answer those questions either. So some of the regulations that have come about are meant to really force the companies to do that kind of measurement and ongoing auditing and monitoring. Thinking about then if computation is a constrained resource, are we really putting it to the best use? I think Miriam touched on that a little bit. If we can make decisions actively about how we're using these compute resources, whether it's to generate high resolution video or is a low resolution okay, or do we even need video at all? Coming from a university context, we might want to think about how we're allocating those compute resources for research versus for more operational kinds of tasks or administrative tasks. And then just thinking about the infrastructure itself, I think there are opportunities for improving the balance of how we're using energy and water for these kinds of tasks. Trying to get data centers to use more renewables and to integrate that into the mix that they're using to power and their activities. If we can encourage them to use more renewable energy, smarter scheduling of AI workloads. So trying to schedule things, if you have that discretion over when the operations need to happen, could it be at a lower intensity time, lower demand time of day when you're scheduling some of these things versus when other people, residents, might need more of the energy that's available on the grid. And then finally, just developing more energy efficient AI models and hardware. So really looking at the hardware, the chips, the chip architecture itself. How can we make those themselves more energy efficient than they are now? So I'll touch on a few of the regulations that have come about in California recently. This one, and there's a lot. I should say that there are many, many bills that are being presented. I think at least 20 or more in the last legislative session just here in California. This was one that was actually successful. It went through both houses of the legislature and was signed by the governor. A lot of the interest of the legislators are for their constituents and being able to protect them from the rate increases that they're seeing because of the large energy demands of the data centers themselves, that those costs are in some ways being offloaded onto the consumers and ratepayers in the neighborhood. So that's what this piece of legislation was intended to address, to make sure that the data centers are not being subsidized by the ratepayers. So it kind of walls off the data centers from the other ratepayers to try to protect the regular consumers. And so this piece of legislation requires that the CPUC studies this data center demand and to try to finally prevent this infrastructure cost from being shifted onto consumers. In another piece of legislation, this is by Assemblymember Rebecca Bauer-Kahan, she similarly wanted to make sure, originally she just wanted to make sure that California was going to have the energy capacity to meet the needs of these tech companies. And so she was going to the tech companies and saying, just tell us what you're using so that we can better plan what we're going to need as we're doing this future planning for the electricity grid. Of course, the tech companies were also not happy about that. They felt like it was proprietary information to their own companies and were very reluctant to share it. But this legislation would have required the Energy Commission eventually to require efficiency constraints for the data centers. Mostly it would just create this visibility into the energy footprint of these AI companies and the different models. There's also a distinction between the energy that's required actually for computation and the energy that's required for cooling and managing the centers themselves. So at this point, about 60% of energy that AI that a data center uses goes for that computation itself, and about 40% goes to the cooling. But that's another ratio that people are going to be looking at more closely, like this idea of the power usage ratio is going to be further in discussions. But it died in committee because there was quite a bit of industry opposition there. So that one did not make it out of committee. There are some other newer proposals. This one comes from the California Senate, Senator Jerry McNerney. And here again, he's trying to prevent the ratepayers from paying for the development of the data centers. In this case, he was going to impose a surcharge on high consumption data centers and then use that revenue to reallocate to the ratepayers and offset electricity costs. So this one is still in committee. There are about a half dozen or so of these bills that were in discussion just last week in the committee. In the Senate, it was on energy, utilities, and communications. That was the name of the committee. And so there are a few other bills that are still being considered there now. And finally, this was another one aimed at getting an understanding of water usage. This was another Assembly member, Diane Papon, who proposed that data centers share their water usage and estimate that before getting a building permit. So you'll see it all the steps along the way of building a data center, of running and operating a data center, that the legislators are really looking at where are the prime insertion points where we can see to try to get a basic understanding of the demands, both water and energy, and then to address that somehow to protect the ratepayers, to protect the environment. And these are some of the strategies that are being used. Again, this one passed both houses of the legislature, but it was vetoed by the governor. I imagine we'll see more bills like this coming up in the future, though. So here, this is a fun interactive map. If you haven't seen it before, the URL is at the bottom, datacentermap.com. So you can go in and play with where these data centers are being proposed and built. And there are quite a few, as you'll see in California. And then, as was mentioned, there's been a lot of opposition, specifically here in California, but elsewhere as well. And Monterey Park was one of the early places that passed a moratorium on building new data centers in that town. And then again, Imperial County in Central California down toward the south. This data center was actually originally approved and they were about to go into construction. And then there was such a community backlash against it that the city council pulled the permits and said, no, you're not allowed to build it. So now, of course, it's in the courts. And I think that will be going on for some time. But these are just examples of some of the organization that communities are putting together and advocacy groups to oppose building data centers in their area. So what about other states? Here, I just put a couple of other examples. You'll see more activity in Virginia, again, because there are so many data centers located there. Oregon has similar kinds of legislation going on. Nevada, Texas is another state to keep an eye on, where they are also putting constraints around the building of new data centers. In the federal landscape, it's a little bit quieter, as you might anticipate. That Senator Chris Van Hollen, he's a Democrat from Maryland, did put forward this Power for the People Act earlier this year, requiring the corporations to pay for data center expansions. The Federal Energy Regulatory Commission launched some efforts just recently to try to get a handle on load integration. And then, of course, you probably heard about this Bernie Sanders and AOC effort, joint effort earlier this year. The March 25th date was when Sanders introduced it to the Senate, and the AOC just introduced it in the House last week, I think. So again, I doubt that that will actually go anywhere. But these are some of the efforts that are building the headlines that you're seeing around moratoria on data centers. Again, the international landscape, Miriam touched on this a little bit. Here's just a similar kind of graphic that's showing that the US holds over half of the hyperscale data centers. But some of these issues are being faced elsewhere in the world as well. So India, the government was giving all these tax benefits to these companies to build data centers, but then the farmers were up in arms to say, look, this is our agricultural land. You're taking water that we need for agricultural purposes, and that's not fair. That's kind of an implication on food security and other kinds of downstream effects. This is Governor Gavin Newsom. Like I feel for these leaders in some ways. It's Newsom I'm most familiar with, but they have to make a tough decision. They want to protect their constituents. At the same time, they need the tax revenues that these tech companies are bringing. Something like 10% of income tax in California comes from these tech companies. So if they decide to move out of state, that's going to have a real impact on what we're able to do in other areas of social benefit, paying for housing, paying for education. We need those revenues from the tech companies, as dark as that might be. So I think he's really walking a fine line, trying to appease the people who are interested in the environmental impacts and protecting ratepayers, but at the same time trying not to aggravate the tech companies sufficiently that they would leave. So here, just to close, we're seeing this new kind of category of AI infrastructure policy. This is something that's relatively new. We've seen, of course, industrial regulation before, but this is a new kind of flavor of that industrial regulation, asking about who's going to pay for the electricity and the grid upgrades, how transparent do they need to be, and how should they be run? How can we better integrate them into the clean energy and renewables that we have coming online? So I will stop there.
Wow, thank you so much, Camille. That was fantastic. Nice to see a lay of the land from Miriam, and then just the regulatory landscape from Camille. And kind of to close this off, we have Wani Park, who will give us a little bit of hope, or at least, when I first heard about sustainable data centers, I thought, what? What is that? Is that real? Is it possible? Because if in some cases, if this is kind of inevitable, it'd be nice to find some hope and to see what are the possibilities of data centers being good stewards of the grid and local communities, as he puts there. So Wani is a seasoned entrepreneur with only over 25 years of experience in energy, IoT, and software as a service. Wani has incubated and scaled companies in clean tech and sustainability. Prior to founding Pado, Wani was the SVP of Business and Corporate Development at Bidgely, which was also a BECC attendee at one point, global powered AI SAS provider, and the CEO of Zen Ecosystems, a leading provider of energy management solutions to small, medium businesses. I'm going to stop there and let Wani take it away. Thank you.
Great. Thanks everybody. Thanks for having me. Just really excited to talk about this stuff. I'm so interested in feedback and understanding what's happening here because we have a very, I would say from Pado's perspective, a myopic view, right? We're grinding every day. We're working with data center operators. We're working with ISOs and RTOs as well as utilities. And so it's a very tactical approach, but all the comments that Camille and Miriam have made is literally what we live and breathe every day. Just a little bit about, Pado and what we do. We're a subsidiary of LG Electronics, and we work within the white space and the gray space of the data center, which is sort of the infrastructure side, but also where all the compute sits, right? So we see everything that we just talked about: power, GPU, utilization, water, all that stuff, cooling, et cetera. And so, the view that we take is that, whether it's the grid, whether it's data centers in general, they are incredibly under optimized, right? The utilization against their nameplate value is very low. And if you even take sort of power in general, right? I'm based in California, 95% of the year, the grid is only, 30% utilized, and then it sort of trickles down. There's incredible leakage. Even when it comes to GPU utilization within the white space of the data center, you're looking at like 19% utilization against the nameplate, right? And so the point is, if you were to speak to hope, right, there's a lot of upside. There's a lot of headroom to work with, right? So that's kind of what we do every day. Um, you know, I think what we've also heard, today is there's like this massive chasm, right, between all the different stakeholders, right? Whether it's the ratepayer, whether it's, regulatory, whether it's data center operators, the grid, et cetera. And what I would say is that, and I'm just going to use this quote from F. Scott Fitzgerald, is that, we've seen this before, right? I mean, I don't know how far back you all go, but I remember when under the Obama administration with the 2008, I think it was ARA funds to roll out the smart grid. I remember seeing the same sort of thing. Oh my gosh, these smart grids and these meters are going to spy on me. And, I'd go to city council and there'd be all kinds of like crazy stuff happening, right? So we're seeing a little bit that maybe it's magnified a bit. But I think the point is that, you could look at it from one perspective where this is like the most incredible, economic growth, community opportunity to drive growth. And on the flip side, like we've all sort of talked about, is like there's all these other things that we also have to sort of mitigate. And more than anything else, I would say, I'm so glad that my stats actually mirror Miriam's. I think they're almost exactly the same here in terms of growth. Is there's an element of time to power is the nucleus of the issue, right? Both on the growth and upside, but also in terms of like, how do we actually manage sustainably that level of growth? And there's so much stuff around that actually, is sort of, underpinning this. Um, what I'll sort of jump into, and I'll double click on, these three levers, right? Flexibility, resourcing, and then just sort of community involvement. One thing I'll sort of just lead with the lever one on the grid is, I kind of spoke to the white space of the data center where all the GPUs are and things like that. In essence, when, being an energy guy, and I'm relatively new to the data center side, right? It's only been about 3 years. But within the energy side, I mean, this is no different than the duck curve. This is no different than non-wires alternatives in terms of expanding the shelf life of your CapEx and infrastructure and things like that. And all the data is there, and the ability to actually manage that both temporally and spatially. And these are mainly through jobs, like this is the inference jobs or the training jobs aligned with power and cooling. There's incredible capacity that actually is sort of underneath the hood, right? And so when you start hearing about, moratoriums, and you start hearing about, oh my gosh, like there's this gigawatt sized data center in Louisiana that Meta's going to build. You gotta take that with a grain of salt, because I think Camille, you had mentioned there's like 4,200 data centers in the US. 80% of those are actually legacy data centers, right? They already exist. We're not talking about the new ones, right? And so there's all this sort of resident capacity that we can play with. Um, the other thing I would add, in terms of lever one is, there's, great organizations out there. We're part of EPRI's DC Flex, and, we exist, in terms of the grid, the developers, the startups like Pado, to actually create a blueprint for sustainable data centers, something that can be repeated globally, right? That actually accounts for all the stakeholders that we're talking about. So that's pretty exciting, and we're seeing some pretty good outcomes coming out of that. I think we've talked about cooling and how important that was. The stat I think I heard was like 60% was cooling. I'm sorry, 40% of the data center is cooling. 60% is GPUs and other overhead. And we see that. And the way to look at it is it's a full balloon squeeze, right? If you can be more effective and precise with cooling, you can drop the energy usage on that cooling, let's say to 35%, 30%, reallocate it to sustainable measures. It could be reallocated to storage or renewable resources. There's a way to actually balloon squeeze that to create more sustainability. And that's happening today. All right. So a little bit about how this all sort of looks from my perspective. more than anything else, when you start talking about economic development and, different stakeholders and moratoriums and things like that, flexibility is a really tricky thing to talk about. And maybe the simplest way to talk about flexibility is, if you're basically selling back to the grid. So let's just say if data centers were all part of a flexible grid program, selling back to the grid through, like, let's just say demand response of some sort. What I will tell you is that that cannot happen today. And the reason why is that the economics don't make sense. And there's a couple of things that maybe I'll throw out there, and I don't have it on the slide, but I'll sort of voice it over. Most data centers operate under a 5 nines uptime sort of SLA. And what that means is that, 99.999% uptime. That means they can only be down 5 minutes a year, right? And so one of the things you should think about is, what if it was actually 4 nines or 3 nines, right? Can you do that to actually create, still the value that the data center operators are looking for? And what that means is, like, you go from 5 minutes to about 50 minutes when you're at 4 nines to, 7, 8 hours when you go to 3 nines. Like, I forget the exact math, but it's something like that. And what that allows is flexibility, right? And the thing about flexibility in terms of being able to sell it back to the grid and being more of a better grid citizen, and saying, yes, I want to be part of the grid, is that the numbers are very difficult, right? So one thing I'll give you, and this is again just sort of ballpark, but in ERCOT, right, the cost or the value that is provided by data centers, right, to sort of like these different labs would be about $2,000 per megawatt hour, right? From a flexibility perspective, what are you getting? Maybe $20 to $30 per megawatt hour, right? So you're looking at almost 100 times gap, or a multiple. To take that even to a more extreme level is that if you're doing like frontier lab stuff, like sort of like the, I don't know, GPT-5 or the latest Claude Opus, model, you're looking at $50,000, $60,000 per megawatt hour. Like, that's the amount of value that these data center operators are actually delivering. And so if you think about sort of like these companies also are looking to go public and they have investor returns that they have to deliver and things like that, there's a big gap, right? And so just wanted to kind of give that as a framework for some of this stuff. Now, the other side of it, we're talking about cooling and sustainability, is that, I think Camille mentioned PUE, right? And so that is really like the God KPI when it comes to data center operations. And what it really is it's basically total facility energy divided by IT energy, right? And so when you want to get super efficient, you're getting as close to one as possible. And, you'll see different metrics there, but a lot of the data centers that we work with, we're looking at, 1.8 to 2.2, things like that. So it kind of goes back to my earlier point against the nameplate value. There's a lot of leakage. So through software, through services, through different things, can you become more efficient? And if you are, getting closer to one, basically you're being a better steward of water usage. You're being better about, energy usage. You're probably aligning with different renewables and different resourcing to make sure that, you're on 24/7. So there is a concerted effort to do that. And as you get closer to one, you actually deliver a lot more sustainability. One last thing I'll add about just cooling in general, right, as you get to direct to chip and immersion and more like precise cooling, is that, when you look at these inference jobs and you look at these training jobs, to use an accounting term, they come into the system FIFO, right? First in, first out. So the analogy I typically give is, like, let's say you have like a bucket or like a glass, right? And you have a giant rock going in that glass, and you have a bunch of sand, and you have like mid-sized rocks. What you have is like all these gaps in that bottle or that glass. That is the inefficiency, right? So if you were to repack those jobs and do it more effectively, you can actually align it with cooling. And you don't need to spend a ton of money on CapEx. You just need software that says, hey, job A of a certain type goes here, job B goes here, and you actually increase the yield like quite significantly. And so it's not really being done. So another way to become more sustainable. If you track the world, right now when it comes to time to power and different things, there's a lot of companies that are making investments, startups that are coming out of stealth. Furbo just went public, if you follow those guys. There's a lot of work that's happening in terms of, different types of sustainable resourcing. And, I would say that, yes, lead time may be a little bit longer, but, there's an element of catch up that will happen. So that's pretty exciting. I'll just throw out one thing that I found kind of funny and interesting is, like, at least around advanced nuclear, I think the Gallup poll did a recent survey, and I think almost like 2 to 1, Most people would rather have nuclear power plant in their backyard than a data center. So I don't know what that means. I don't know why people say that, right? But I guess it's really, we're not doing a good job as an industry to communicate, right? I know personally, I'd rather have a data center in my backyard than a nuclear power plant, but that's just me, right? So. Okay. Some other things that I wanted to share is that, this is just one piece of it, right? But just to kind of recycle, upcycle, and kind of go full loop in terms of value, we have customers that are actually doing some of this stuff, right? And one of the things I would say is waste heat, right? Becoming an opportunity to drive community warmth. One of our customers is it's a Bitcoin mining company, and they are transitioning to becoming an energy company. And I think they are heating 15,000 homes in Finland. I don't have that up here. It's not the Google project. It's a different one. But there's elements of like trying to figure out how do you become more efficient? And this is also almost the inverse of the PUE to kind of create, more sustainable measures and metrics. I would say outside of iMasons, I haven't seen a lot of folks like trying to create these standards. And maybe there's a better way to do that, right? In regards to the industry saying, hey, there's other byproduct positive effects that we should be focused on. Okay. I think, Camille talked a lot about this, and, I think there was an element, I think you mentioned the FERC show cause order that just came out and things like that. But I guess my thing is that there is actual true and economic value in building data centers. And maybe not to get too fancy, what I would say is, the amount of construction and labor, that is actually one of the biggest bottlenecks outside of time to power, right? And when you talk to EPCs that are actually on the hook for delivering the actual physical infrastructure, these are not temporary jobs, right? These are 3 to 5 year jobs, high paying jobs. There's a lot of economic development that's happening. And I think one of the things that, you're going to see is that like through the course of moratoriums and things like that, what you're also seeing is like there's a lot of inlanding going on. I think Camille mentioned there's a lot of, density in Texas and in Virginia. We're seeing folks that are trying to figure out, hey, is there power access in Nebraska, in the Midwest, other markets that aren't key, infrastructure states? But, there's an element of like, we're going to take the business, that is favorable in terms of those environments. And so there's a little bit of that. And I would also add like, internationally, I know like China and probably the US dominate in terms of data center, but there's also like a lot of sovereign AI work that's happening, globally. And so there's an element of competition, in terms of being left behind. And a lot of that compute will go, across borders. Okay. Just really quick summary in terms of, what a good sustainable data center looks like. There's a lot of this stuff, a lot of positive reporting. Liquid cooling technology is going to be really great in terms of water and efficiency, things like that. And, I would say that the industry, there's probably an element of like, they're just taking. I think most of these folks are trying to figure out how to be good stewards in general. So you will see some of these hyperscalers really focused on sustainability, paying their bills, making sure that it's not a negative impact on ratepayers, things like that. And it's just early too. That's the other thing is like, we're pretty early in the cycle. So I would just say, keep at it and, just let the industry sort of, normalize a bit and hopefully we'll have some good outcomes. And I think that's all I have. Just some summary on some of the resources. So that's it. Thank you.
Great. Thank you so much, Juani, and to all the speakers. I think our intention here was not to answer a question of AI good, AI bad, but to just really open it up for a lot of the different issues here. We just have time for a couple of questions. I'm going to point at this one. Do you have recommendations for how workplaces can responsibly use AI tools on an as-needed basis? For example, are there ways to turn off default settings for document summaries as these queries add up unnecessarily? Anyone have thoughts on that?
Maybe I could just jump in. At UC, we have been thinking a lot about AI applications in administration and operations, not only on our campuses, but also in our health systems. And so part of what we're trying to do is to create a baseline training for people to understand a little bit more of the AI systems that they're using. This doesn't exactly answer the question, but I think the more that we see these trainings available, that it could include some of that guidance as to how to take into account what are more or less energy intensive practices in the settings that you mentioned.
Great. And I just wanted to add, I feel like there's the environmental issue, the land issue, water, energy, but it seems like there's also a power issue. And Miriam, you alluded to this in terms of the injustices when people have a data center put on them. And I wondered if any of you have a comment on how do we engage communities? How do we give communities a voice in this? Easy question to end the seminar with.
Well, I think a lot of it has come to these city councils or to county level governance who are making the decisions about permitting. And that's where we're seeing a lot of the pushback from these community organizations who are saying now, not in my backyard, and really pointing out the detrimental effects to the community. So there are a number of different jurisdictions, both on the kind of nonprofit advocacy type organizations versus the counties or local governments that are making the decisions.
Great. And with that, I think we are out of time. So thank you again for everybody who attended. A lot of wonderful chat, a lot of great fodder there in the chat and a lot of great questions that we didn't get to. So thank you very much. Look for the next webinar in September and then the next BECC gathering in July. Really appreciate everybody's time.